Hello and welcome back to Precalculus1. This is the second part of our 3.5 exponential growth and decay, and we will be talking about decay. So today we're going to take a look at the formula when k is less than 0. So let's take a look at decay problems. Now those are very important across the board for many applications, some of which are carbon dating and some are radioactive decay, garbage decay. Then in the medical field we have a whole bunch of ways to apply this using metabolizing drug in a body, in a system, and so on. So there is a lot of ground to cover, from medical to environmental to history and so on. So technically anywhere where you get a loss in some sense. So you have growth when you are gaining stuff like money, right, is accumulating because of the interest. Population is growing over time. And so we did those problems. Now we want to look at a decay situation. Now let's go all the way down past all of these cool calculations we had as a Newton's law of cooling, where we baked the chicken. It was 3 hours and 13 minutes for the chicken. That was some mighty chicken. Anyway, decay problems, where we have y equals a e to the kt, where k is less than 0, and the graph is like this in time, going through our value a, right? That's the y-axis. So these are our decay problems, k less than 0. Okay, so let's take a look. Before we do anything, we have to define a term and understand something that you will be hearing of in every single problem. And that is the concept of the half-life. Half-life. Denoted by lambda, like this, half-life. And half-life is the time it takes for mass m to decay to half of its start value. Half-life is the time. We have to understand that half-life is the time, so t equals lambda will be called the half-life. So the meaning is, if you have something that is decaying, and I don't care whether it's organic or inorganic matter, it is a radioactive element or whatever it is, right? It's decaying, it's losing mass. Half-life is measuring the time what it takes to lose half of its mass. So if I take my formula y equals a e to the kt and transform it into my mass equation, which looks like this, hey, it's the same. I just dressed it up. We want k to be less than 0 for decay. All right. So now, lowercase m, you can say, of t is the mass. capital M is initial mass, and I call it earlier start value. So you can connect it up there to the red. Start value, initial mass. There we go, fixed. Now I can get rid of this nonsense. All right, T time, and the time, you have to use appropriate units. Seconds, years, right? Depends on what you're doing. Certain things decay in a matter of seconds or fractions of a second, and certain things decay for tens of thousands of years. So, like plastic, all right? So, time will be appropriate, right? Unit of time will be appropriate to the problem, and that's usually given, right? Because it says what the half-life is, and you just take those units, right? If the half-life is 1/2 of a second, then all of the other times in the problem will be done in seconds, because half-life was given in seconds. So that's something that you just have to pay a little bit attention to, and you'll be fine. And k is a constant, right? Less than 0. Cool. So we can first develop the formula for half-life, even though you can just run through calculation every time and figure it out. So at t equals lambda, half-life, we have mass equals to initial mass divided by 2. That's the definition. What's happening at the time of the half-life? Your original mass decayed halfway. So whatever is decaying, it lost half of its mass. So now plug in. We have m equals me to the kt. Plug in t equals lambda, and m equals capital M over 2, because it's a half now. So we get m over 2 is equal to m e to the k lambda. Divide both sides by capital M, which is a non-zero number, because you have to start with some mass. You can't just start with nothing. So we go and we say some mass m, whatever it is, and now this becomes 1, leave some space, so 1/2, leave space, e to the k lambda. Your job is to solve either for lambda or for k. It doesn't really matter, formula works both ways. So you ln both sides to kill off the exponent e. So ln of 1/2 is equal to k lambda. From here, you can write that lambda is equal to ln 1/2 divided by k, or you can say k equals ln of 1/2 divided by lambda. Generally, it's the one on the bottom we need, because lambdas are kept in tables. If you go to a page for medication, you go page for radioactive elements, you go write any kind of material, they're going to give you all of the half-lives. They're all listed, right? Advil has half-life of 1.9 hours. biological half-life of 1.9 hours. So we will see the dosing later on of Advil. Pick medication, it doesn't matter. Advil is the one that I know by, off top of my head, because that's the problem that I solved most of the time. There was aspirin also in couple of problems here and there. But you can look up the half-life of any drug out there on the market. That's all available and online. And I think if you use actually Wolfram Alpha, you can. That information is part of the information about the drug. And yes, you can take Wolfram Alpha, which is the math software, and type Advil in, and you will get a lot of cool info on it. You can do the same with the orange juice and bagels and stuff like that. Everything is in that database. Anyway, so now we have developed the formula which calculates either lambda or it calculates K. Generally, we need to calculate K because lambdas, as I said, are given in the charts. So now that we understand that lambda is something that is called a half-life, and that lambda half-life is the time in which the mass decays to half of its original value, of his initial value, you can literally think of it this way. Take one of those expo markers that we have at the, that we used to have lying around next to the whiteboard, right? So, and hold it, in your hand, in your mind's eye right now. It is measured by students, because it was one of the project questions at one of my earlier years. Students went to the chemistry lab, right, and used those very precise scales to measure that it's 16.2 grams of mass. So that's primarily plastic, so you can think of it as 16.2 grams of plastic in that one expo marker. Then they did the research to see what type of the plastic is used to make that, and found also what is the half-life for that plastic as well. All of that stuff is publicly available, obviously. So now they have initial mass of the marker, they have the half-life for the plastic, for the material that is made out of. So what is the half-life? Half-life is the time in which that 16.2 is going to decay down to 8.1. And whatever that takes, 10,000 years, 7,000 years, 16,000 years, right? And that's the half-life. So that's what the half-life means. The marker will decay half of its mass. Decay of atoms happens spontaneously. We don't need to have radioactive material to radiate energy and decay on the spot. Obviously, highly radioactive materials do that. But everything decays. Our bodies decay. Hey, that's aging, right? So the bodies decay. Everything is decaying at a different rate. So going down to these formulas, it's the red one that we need most of the time because lambdas are known. Okay, so let's take a look at some of the problems that you might run into. So generally, the fields of study would be archaeology, because you dug up something from the ground, and if it was of the organic nature, you can do what we call the carbon dating, and the carbon dating can tell you how old that object approximately is. For instance, if you dig up a book or a painting or a scroll, right? All of that stuff was made from trees and plants, right? So they contain carbon isotope C14, which we know the decay rate for. So you can use, in a lab, you can extract how much carbon C14 is left in a small sample that you pick, and then from there you have lambda because it's known for that, and you have the percent. You can actually work out the time. Now you have to be a little bit careful. Obviously you can't carbon date something and say, oh, okay, so this thing is coming from, date so and so hour and a second. No, that doesn't work that way. It works the way that you say, well, the tree that this scroll is made out of is, 2,000 years old. Now, you say 2,000 years old, right? So the tree, was a sapling 2,000 years ago. Now, you don't know if that tree was harvested 30 years or 100 years, right? There are trees that are 150 years laying around the planet, right? So we can do absolutely amazing job of pinpointing something, right? But we can do a pretty good job, right? So think about that. Other than that, we don't really have other methods. But it has to be organic. So you can't go and dig up a little stone and see how old the stone is, because it's just going to go back to the creation of the planet, right? When all of the dust was swirling, right, in gravitational field. So we're not going to go there, right? So you can't carbon date, for instance, pyramids, because they're made out of stone. What you can do is you can carbon date the bones that are laying around. You can carbon date if you find some, you dig up dishes and things like that, the old wooden tools, jewelry that was painted with organic colors, paints. If you think that if there's anything painted on a structure you want to carbon date, hopefully that paint was produced within the same time period like the building, because plants are made out of flowers, right? So you can paint, right, pigments. So there are a lot of things that you can do with this. Now let's take a look at the carbon dating problem. Try to find something that says, how old is And now I am trying to find one problem. Just give me an hour. I'll be right with you. Okay, here. So, problem 16. It says, initial mass is 16 grams. And so initial mass, we are dealing with carbon C14. And we have how many grams of carbon C14 are left 11,430 years later. Put the word years. And half-life of C14, I need to find that because they gave us a different piece of information which I didn't like, so I didn't talk about it. There we go. 5,715. 5,715 years is the half-life of carbon C14. All right, cool. Let's do the problem. The first business here is to calculate ln 1/2 divided by 5715, which will give us our K. Now, remember to keep 4 significant digits. That is your job. So now, let's see, 1/2 divided by 5715 gives us 0.0001219. So if you are keeping 4 significant digits, you do not count these. They are not significant. These are significant, right? So you could have 10 zeros in here if the calculation, right? None of them count. All right, so now we have our, this is going to be negative. I forgot about that. Sorry, forgot that negative sign. There we go. It's a decay. And now we have our mathematical model. M equals ME to the negative 0.0001219 T. So this over here is our math model, exponential model. For C14 decay. What is the question? The question is, if the initial mass is 16 grams, how many grams will be there after 11,000 blah 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 years? So mass is equal to 16 grams e to the negative 0.0001219 times 11,430. There we go. Punch that in a calculator. Oh, I see that you guys are not reading the calculator. Uh-oh. Okay, let me just finish this. 16 times e raised to the point. Oops, forgot the negative. Negative point. 1, 2, 3, 4. No, not 4. 3. It's supposed to be 3 zeros in here. 30, there we go, 1219 times 11,430, close parenthesis, there we go, 3.972, so about 4 grams left, all right, of carbon C14. If you're starting with 16, you will have all of this. All right, so now I noticed that you guys are having issues in reading the calculators, the values, and that will significantly impact your ability to operate in this section. The calculator value, when you type in ln of 0.5, because that's your half, close the parenthesis, divide by 5715. So this is the way you plug in the formula. getting the digits 1212855, that's correct. So the answer of 0.800124, that answer is not good, and probably you did not close the parenthesis, or something was typed incorrectly. The other two are good numbers. The calculator returned negative 1.212855, but then there is this e negative 4. This over here is scientific notation, which you guys should have studied in intermediate algebra. When you are dealing with scientific notation, you are only allowed to have a 1 digit and then decimal point. You must have only 1 digit. So I'm going to round this now. This 5 makes 8 into a 9. And then write this as a times 10 to the negative 4. You might, right? So this is the way the calculator writes 10 to the negative 4. And this is going to be 0.000. So if this is a 4, you will be making this to be your 4th decimal. So that's where the 1 goes, and then just a string of these 2, 1, 2. Oh, I just noticed that I used 5. There was supposed to be, okay, so in a problem over here it's supposed to be a 3, not a 9. Really? 1, 2, 3, yeah. That was supposed to be a 3. That was supposed to be a 3. That was supposed to be a 3. And let's see if I go and do the calculation again. Second entry. And change this 9 into a 3. Oh, we get 999. So that is a 4 grams. 9993. So 4 grams left. So be very careful when you are dealing with these problems, because the calculator will give you this at the end every time. Oh, don't feel bad about it. Don't feel bad about it. This is something that is worth mentioning right now, and your questions are welcome, because you need to pay attention to these kind of things. These are not calculations you have done before. So from intermediate algebra, and by the way, in intermediate algebra, this is the way you used to write it. Now calculators write it this way, so it's okay to miss it. But now, on the second example, not okay to miss it anymore. All right, let's go and work out a nuclear example. We are going to let some uranium, plutonium, or something. Let's see what cool thing we can. Ooh, look at this. Radium, uranium, arsenic. Wow, arsenic. It's a poison. Half-life of 17.5 days. Yep, autopsy is definitely going to show that. Calcium 47, 113 minutes. Calcium 47. Sorry, 113 hours, not minutes, hours. Anyway, let's take a look at uranium, because it's so cool. Actually, I have even better example. No, let's do something much better. Doormat, and I drew this smiley face with his teeth, is because it's fitting. Doormat is a very interesting toothpaste that goes all the way back to the Second World War. We're talking 1940s, 1942, 1943. If you do a quick search on Doormat in Google, you're going to come up with a lot of pictures with a tube and so on. That particular toothpaste was very, very special. It is the first toothpaste on the market for teeth whitening. Yes. So you buy Doormat, you use Doormat, and your teeth are brighter and whiter than anyone's teeth ever before, and then you die horrible death, right? Why? Well, the Doormat was using the radioactive element called thorium, isotope of thorium-229, that has a half-life, something ridiculous. Let me check this. Let me check this real quick. Thorium-229 half-life. Let's see what we get. 7,340. Yes, got it. 7,340. Wow. Cool, huh? So, this toothpaste, the first ever teeth whitening toothpaste, which was advertised as the radioactive toothpaste for teeth whitening, was laced heavily with thorium-229. It made teeth glow bright white, so it was by far the strongest teeth whitening toothpaste ever produced. Well, the problem is that the rest of the body dies quickly off of the deposits of thorium. So a lot of people died. Well, everyone who used it died within a couple of years. And then you can, if you scroll enough on that page with posters for Doormat, you will find the posters warning people to stay away from Doormat. Right, so technically everything goes like that, right, with what we make, right? Advertise, and the people start using it, and then, yeah, but we figured out that we continuously bleed from our left eye forever. Anyway, so Doormat was that. So now what I want to do is I want to take a look at how much thorium is still on these corpses, on their teeth. So it's been 1940 all the way to 2020. Let's click this on 50. Let's click this on 50 because if they bought the product in, I don't know, 1943 and they used, and then by the time they died and so on, let's just put this because this gives us 70 years. 70 years. What percent of thorium-229 is still there on their teeth? What percent of the thorium they applied? Some people brushed once a day, some people brushed twice a day, some people brushed, well, it's 1940, some people brushed once a month, right? Whatever. So the question is, what is the amount of thorium left percentually, right? Percentually. Well, the first order of business is to figure out our K. And that's going to be our ln of 1/2 divided by the half-life of 7,340. That's going to be negative 0. Now you will go into ln of 0.5 divided by 7,340. And we will get times 10 to the negative 5. So 4 zeros here. And then 9,443. There we go. Now that I have K, I have my model for thorium, which is the toothpaste in this case. There we go. So this is the model. And what do I want to know? I want to know the percent P of M, of capital M, of initial amount brushed. So what is the percent left when T is equal to 70 years later, because my half-life was in years as well. So I will have P times M equals M e to the negative 0.0000944 times 70. So this over here is the percent of initial mass. That's what the setup is for. P stands for the percent. That's going to work out obviously in decimals. So we'll see what the percent is. And it's of initial mass, so of is in mathematics is multiplication, and the capital M is the initial mass. Now we see that that cancels, so it doesn't matter whether you brushed once, twice, or 5 times a day or a month, right? You put some amount of thorium, and that whatever amount you have, or whatever amount they had, right, is going to decay at the rate. So it's not that if you have more, it will decay faster. If you have less, no, right? Decay is the decay regardless of how much you have. So my percent P is simple calculation of e to the negative, and now we multiply these numbers. So this times 70 first gives me 0.0066103 blah blah blah. So now I go second E caret, second answer, and we get, careful with the notation, you can't use both. It's either decimals or it's a percent. So the answer is 0.993. So that transfers to 99.3% left. These are the best looking corpses by far. I mean, they have a bright white teeth. These people died 70 years ago. They still have 99.3% of thorium left on their teeth. So welcome to Decay. Let's take a look at Advil. If you go to, let's say, Wolfram Alpha, I'm waiting. What am I waiting? Let's see. Oh, well, M's canceled, right? So M's are gone. And when you cancel those M's, you get this. And you punch that in a calculator. So percent is equal to this. but it's given as a decimal. 1 is 100%, 0.99 is 99%, going down. So I have 0.99, which gives me 99%. And by the way, this calculation, that's that number, right? When you multiply by why are we multiplying by 70? Because it's been 70 years of decay of thorium. Oh yes, it's above division sign. So you have to use the second. All right, so now the next order of business is to hop real quick. Yeah, use the second and then division. Yep. Can we get Wolfram Alpha? Wolfram Alpha, perfect. And all I'm going to type here is Advil. Let's see what we get. There you go. You get the formula. You get the name, ibuprofen. You get all of the chicken fences and things if you want to cook this at home, I guess. Go down, go down, go down, go down. The drug categories, dosage. There we go. Look at the bottom of the screen now. Biological half-life 1.9 hours. Right? Biological life 1.1. You can type any drug you want, but as I said, usually I go with Advil. This is a sponsored video, obviously, by Doramed and Advil combined. They sponsor all of my education. Like and subscribe and and hit notification when I teach differential equations. You don't want to miss that one. Anyway, so we have Advil over here with biological life of 1.9 hours. And I want to calculate percent of Advil left in the body after 4 hours, because people usually keep popping dosage every 4 hours. So I'm going to say, let's see, what's left after 4 hours. So the dosage. Oh, I took 2 pills, I took 3 pills, mine are 200, mine are 400, mine are 500, right? That always cancels out, because we are going to do the percentual decay here, and then you can multiply whatever milligrams you took by the percent to see how much is left, right? So we're going to calculate problem in general, and then you can apply it to a particular case. So we have our K calculation, which is ln of a half divided by 1.9. That is our standard way to start these problems, where you go ln of 0.5, close the parenthesis, divided by 1.9. That is going to give you negative 0.3648. And now we have our mathematical model for Advil. You are interested at the percent left after 4 hours. Guys, that's the same calculation as the one above when I looked for the percent left on the teeth. So that's percent of initial value is initial value e to the 0.3648 t. T is now 4 hours. M's will drop the same way they dropped before, and we calculate our percent when we figure out this value here. So this is going to be e raised to the open parenthesis negative 0.3648 times 4 close the parenthesis, and we get 0.232. This means that 23.2% of initial dose is still in your body. Then you take another full dose, and what is that full dose? 100%, which means now you're ending up with 123%. And then the next one, and then the next one, right? Every time when you take a full dose in the periods, right, it increases the dosage in the system. Now, certain drugs create dependencies, damage other organs, and all of these kind of things, right? So you have to be very careful with this. But you have to understand that half-life of 1.9 doesn't mean that it lost half in the first hour and lost a half in the other, right? That's not how exponential works. It loses half and then loses half of the half that remains. So half of the half it remains. All of the calculation errors, most of them are because you don't close the parenthesis. Or didn't put the caret, or there are a whole bunch of things that could go wrong. The calculation over here is definitely good. Just make sure you are closing all of the parentheses in a calculator and calculating one thing at a time. So now, if I want to, do a crude calculation, let's say you took 500 milligrams of a medication with a half-life of 2 hours, dose every 4 hours. What is happening? Well, if you took up 500 milligrams at time equals 0, there is 250 milligrams at time equals 2. There is 125 milligrams at t equals 4, right? Because you lose half of what's there, and then in the next 2 hours, you are losing half of what's there. Well, now what's there is 250, so you are losing half of 250. You are not losing the second half of 250 from 500. No, this is like a completely new problem now, right? It resets, and it says, the next 2 hours, I'm losing half of this amount. But at time t equals to 4, you pop another 500, right? Because it's the time for the new dose. So actually at t equals to 4, you are at 625. That's t equals to 4. So now 2 hours passes. It's half of that, which is 300,125.5. That's at t equals 6. And then at t equals 8 hours, right, t equals 8 hours, you are losing half of this. That's what? 156.25, I hope. But then what's happening at 8? You pop another 500, new dose. So T equals 8 is actually 656.25 milligrams. Do you see that as you go from hour to hour to hour, the dosage constantly increases, and every time you take the dose, it's actually way much more than what you took the previous time, right? It accumulates in the body. Now, some medications you have to gradually get off of it, so there is no dependency and the cold turkey and whatever else are there. Another thing to keep in mind over here is the exponential decay graph. This is your time, this is your x in milligrams, and this is the exponential decay with your initial 500 milligrams you took there. And you took nothing else ever. That was just one time only. You were 7 and you took one pill of one thing. What do we know? There's the question in the chat. That's my question. How long? You tell me. Look at the graph. How long does it take for it to fully clear from your body? Mathematically speaking. Come on, write it down. What do you see in the graph? What's the end behavior of exponential function that it's in a decay mode? Come on, when is the exponential function going to touch x-axis? Never. Very good. It doesn't ever touch or cross x-axis, so it never in a lifetime goes away. Now, obviously, it decays to such a minuscule amount that we don't have the tests to detect that. But if our technology wasn't so primitive and bad, you would be able to trace everything you ever took, ever, right, at any point of your life. If we had tests that are good enough and sensitive enough to do this. Because go ahead and try and figure out now, you can play with this stuff, right? Say, I'm 7 years old and I'm going to take 500 milligrams of Advil. How much Advil percent-wise is there in my body 70 years later? So now you're 77, 70 years has passed. How much of that pill that I took when I was 7, right, percent-wise, is still in my body? So this decay is, mathematically speaking, never going to go away, but it actually is going to go away, speaking, from the reality perspective, because we are supposed to talk here about the molecule of right. So when these molecules, there is a finite amount of these molecules, which is so it's gonna go. All right. What else can we do? Pick a date. Yeah, just sometimes next week. I mean, we only have 2 weekends left, and right, next one and the following one, and the course is over. So the sooner the better, but then you guys need time to practice all of this stuff. So we did medical, we did carbon dating, radioactive. So I think we got them all. Maybe can I find anything with problem 31 is giving you Xanax. In problem 31, and aspirin in the problem 30, with their half-lives. Aspirin of half-life of 12 hours, Xanax with a half-life of 36 hours. Those are the two that they have in a textbook, so you can go and take a look at those. All right, so now we are going to take a look at another one of these problems, except this one is going to be the logistics problem, and it's talking about coronary heart disease, where you can look at this model and come up with various numbers that you might be interested in. Now, guys, we're talking about health professional field, right? So a lot of jobs in this area. There's masters in public health and a whole bunch of stuff that you can do. If you had your master's or doctorate in public health and you were, big shot, now you would be sitting in the White House making decisions, right? So what we are going to do now is, let's say, problem 44, which says that the logistics growth function given as p of x equals to 90 over 1 plus 271e to the negative 0.122x so models the percentage. So this over here is the percentage of Americans who are X years old with some coronary heart disease. Use the function to solve what percentage of 80-year-olds have heart disease. We have 2.5 weeks left. The final should be the last by May 12, May 15 is the final. So we have plenty of time for everything. Yep. All right. So we just need to stick in 80. And that's it. X is how the age. So percentage for 80-year-olds is simply 90 divided by 1 plus 271e, negative 0.122 times 80. And that's 90 divided by, open parenthesis, 1 plus 271e, negative 0.122 times 80. I have extra parenthesis because I forgot to open a parenthesis. This would be wrong. Hold on. Second insert, parenthesis. Much better. All right, let's see. 88.6%. This statistic that we got from this particular problem states that 88.6% of all 80-year-olds have some kind of a heart condition. That's by the mathematical model. Now, you obtain this mathematical model by looking at statistics, right? Because the cause of death is recorded for everyone, right? And a heart disease is a big one, obviously. So it will, it will obviously affect all of this. Cool. So we did many, or all of the problems in this section are word problems. You missed a number somewhere if you got a different value. I just checked this against the textbook. I have the same value as the textbook. So this number of 88.6 is definitely good. Just retrace your steps. You might have forgotten a 1, or you skipped a 7, or you did something, right? This needs to be in parentheses if you are putting in everything in one shot. Or you did it in stages and then you rounded generously, and then, yeah. So, well, 3.5 homework is already posted. You just need to finish off the homework. We did the second half, so half of the problems you guys have there are decay and half of them are growth. So just finish that homework that it's already posted. There will be no new homework added for this section. Now, we are going to cover in chapter 7. We are only supposed to cover 7.2 and then jump to 7.4. And if we have time, go back to 7.3. So technically, we must do 2 sections that are left. So the next class, now 7.1 is something you did in elementary and intermediate algebra, which is systems of equations, 2 equations, 2 unknowns, just x and y, substitution, elimination, graphing, right? So next class, I am going to, on Wednesday, well, first of all, we need to figure out the exam and situation and all that stuff. Anytime when I teach next time, it will be 7.1 to review for about 15 minutes, and the rest will be 7.2. The next class, whenever I teach after that, would be 7.3. So 7.1, 2, and 3. 7.1, just a quick review. 7.2 is what we need. No, and then 7.4. And then if we have time, it will be 7.3. Partial fraction decomposition, which is something that you need for Calc 2 and differential equations. So it's optional section in the syllabus. We might or might not get into that. Those of you going to calculus, obviously, Calc 2, obviously learn that. But, most of us reteach it in Calc 2 anyway. So basically that's what we have. Now, exam. Exam is only on chapter 3. We only have 5 sections, but these sections are some of the most important sections of your life. If you are in sciences, if you're some kind of STEM, you will be dealing mostly with stuff you learned in this chapter. That means graphing, shifting, solving equations, and obviously understanding and setting up models. We have seen that these word problems cover huge variety of problems, from history and archaeology to environmental issues to physics and engineering and so on. And then you have the medical field, and then you have population, which is biology, and you have the also population is going to be politics, right? The overpopulation, right? They implemented one child in China, right? Policy. So I think that's lifted, I think. But public policy is also, right, with the population. And then you have the health field and, public health with the crisis that we have. It's all exponential models that we are looking at, the mathematicians are looking into right now, projecting the number of deaths, projecting flattening of the curve, and so on. I still suggest a number field video on the virus to see, you know, how differential equations give you these values. You don't have to understand what the equations are. You can just see the way to get it, and you can actually, they tell you the software and stuff that you can get for free to reproduce that stuff and play with numbers on your own if you want to, regarding the virus. It's been 2 months already since that video is out. So you have all of these things, and you know, sections 1 through 4 were leading to this, to the word problems. So exam 3, I would say, you know, this weekend might be too soon, but maybe we can do, you know, Thursday through Saturday or something. The sooner the better, right? That's the way I look at it. The sooner the better. I would teach 7.1, 7.2. I mean, 7.1 is a review, 10-15 minutes, and then I would teach 7.2 on Wednesday, and then do review on Monday, and then go back to teaching on Wednesday, have exam Thursday, Friday, Saturday, let's say. And then next week, we just have one section to look at and spend the rest of the time practicing for the final. You know? Yeah, I will open, if you guys, you know, if this sounds okay to have the test starting next Thursday, we can open quizzes this Thursday, let's say. And the exam will be on Canvas, the same deal like you had last time. Exam would be on Canvas, and you would plug in as much as you can in the answers. And if you don't feel like typing the partial credit stuff, just send me the picture of your work. Many of you did that, and many of you did not do that because you were either confident with your grade or you were maybe unsure how to do it. I don't know. But, you know, take the picture with your cell phone and just send it in an email to my regular email. That's it. Yeah, let me see. So, exam 3. Yes, May 7 to 9. And then final. Let's see. When is the semester officially ending? I don't know. I think they said 12th. So 11, 12 to be the final? And we can have a review on 11. Some of you don't need to review. But some of you most likely won't be even taking the final. Whatever. You take the final if you need to, right? Why not do 7, 1, and 2 on Wednesday? Yeah, we have, that's what I said, on Wednesday. Final maybe I should write it down. I don't even know. This is information that we don't need on a public video, but what the hell. So the next class is 429. And then the next class is 5-4. Today is 27th. And then 5-6. And then 5-11. So this is what's left. This is it. Remember that we lost a week during the spring break because the spring break was extended for a week and we lost 2 classes there. Now, we can add extra class on Friday after my differential equations that I had to add in. Maybe we can add one more class on Friday as a review class, let's say. So 429, that's the Wednesday, that's the Monday, that's the Wednesday, that's the Monday. So 7-1, 7-2, it's 7-2 technically. And 5-4, we can do 7-4, which is what we must do. Then we can review for the test the day. See, I don't like reviewing the day before the test because it's better if we review here. Exam 3. And then do 7-4 over here. And then have the review for the final. And then exam 3 is 5-7 through 5-9. And then final would be 5-11 to 5-12, 2 days. Let me check what is the official, if there is official. Because I was hoping they will add back a week that they wasted for the, but they didn't. So now we have to scramble. Yep. Final exam must end on 5/12. So the best we can do for the final is 11 and 12. I mean, I can open it on 10th. It's not a problem, but 5/12 midnight. To give it the most time. And the deal for the final, what the department agreed, is final is optional under these conditions. 1, if you take the final, it counts. Nothing is dropped. So if you take the final, you will have your exam 1 plus exam 2 plus exam 3 plus the final. Second option, if you do not take the final, then average of the 3 tests plugged in for the final. Personally, I hate this because you were supposed to take only the final and no exams or anything like that to just have the knowledge of the course, right, and move on to the next one, especially that Precalculus1 is so important for your future education. But we live in unreasonable times, so this is what we have. You have, so you will log in and either take the final, or you will skip the final. If you take it, it counts. If you don't take it, the average is there. So that's what we have. So that's the situation for this semester only. It does not apply for summer and fall and so on. It is just for this. I am completely lost, or just the final grade. Well, you have to understand that in my class, the exam 3 is weighted more than exam 2, which is weighted more than exam 1. So it's a weighted average of those exams. So just make sure that when you are averaging your grades, you don't go divided by 3. Right? You have to multiply them by the percent and divide into the percent. So if you have 100 on the first exam, 80 on the second, and 40 on the third exam, this one is times 10%. This one is times, what was it? I don't know. I'm just going to put whatever percent, 15%, I don't know, and times 20%. It's a weighted average. So from here, you are getting a 10. From here, you are getting, what's half of 40? 12. And 20%, so you're getting an 8. From this one for a total of 30. But the amount of points was 45. So that's 30 out of 45. So the average works out to be 66.6, so 67, because it will be rounded. So these grades average into a 67 because of the weighted average that progressively gets higher percent onto the... you can rewind the video and go through, with whatever the exact percents are, like 10, 14, and 16. I don't know. But later exams weigh more than the first exam. So this grade would be plugged into the final grade if these are your grades and you did not take. All right, so please so read the announcements. I will post these things in announcements as well, and we'll go from there. The comments obviously under announcements will be open for you to discuss these things as you go along. And the quizzes, well, they open Thursday, right? There is no, right, Thursday, yeah. So let's just open quizzes on Thursday. So that's what, 3 days? I will go now to post, I'm going now to the website, to my MATLAB, to post the quizzes, and they will start on Thursday. So you can put the, info there. If I remember, I'll post about the quizzes. I'm just going to open them right now. So keep checking. Authentication required. I am authenticated. What are you talking about? It says my name. Well, my MATLAB might be having issues. Let me see. Oh no, it works. Okay. It was giving me some weird thing there. But anyway. Alright, so where are the exam 3 quizzes? Exam 3 quiz 1, 2, 3, 4, 5. They're out of the order for some reason, but that's okay. Alright, so I will open all of these quizzes for you. They will start Thursday 6 a.m. and we'll go from there. I will see you all around. Bye.